All right, welcome everybody. This is the Android Platform Anatomy section. At first, let me just ask you one question. How many among you are application developers? Okay, so I'm nearly the only one who is not. So my talk over here is gonna be around presenting you what is actually beneath Android. So all you guys develop application for Android, and there are a lot of people, device manufacturers and so on, who actually does the Android platform. And so what I'm going to introduce to you is what's really under the hood. So my name is Benjamin. I've been working as the Android platform architect, at least that's what I've been doing up to this year. I've been moving around to the cloud now, different experience. I've been designing embedded systems for like 10 years and been working on many open source projects, both as a contributor or as a project founder. So I don't know if you are aware of or ever heard of. I've been the author of the Geeksbox project. I don't know if anybody ever used this one. It's a multimedia distribution, Linux-based, which came out in 2002. Which simply turns your PC into an HTPC. So it's pretty much what XBMC does on today. So we've been designing this 10 years ago, and it was quite a great success, starting about 2,000 downloads a day, which 10 years ago seems quite a lot. I've been doing many conferences, mostly for the Linux Foundation. As I said, I'm designing embedded systems for like 10 years. So I've been presenting to the Embedded Linux and to the Android Builder Summit many things about how to optimize embedded systems, how to design them, how to avoid the different pitfalls that one may come into in order not to slow down your applications. And mostly for Android, I've been designing or presenting different guides and tutorials about how to write not applications, but at least drivers, and how to adapt the platform as to create your own Android device. All of these talks are actually available on SlideShare, so if you just want to have a look, just go over there. This talk is also available on SlideShare, so just hit my name over there. A few references over there. If you are pretty new to the Android application development, I really recommend you to read the Learning Android book from Marco Garganta. This is one really great book that covers the whole application architecture of Android, how to design applications, what are the activity, the services, the content providers, and so on. If you're more into the deepest levels of Android and want to know what's under the hood, then you may have a look at the Embedded Android book from my friend Karim Yagmur. This is a really nice book that just covers all the basics about Android and the internals of the system. Based on these two books, I'm also the author of a huge series of articles that I wrote for the French magazine, Linux magazine. So if you're a French reader, which I assume 95% of you are, you may just have a look at the different publications that I made over the last year, and it presents many things about how Android works, what is the initialization system, how the graphic works, how the audio works, the networking layers, and so on and so forth. So, as on today, as I said, I'm going to introduce you to the Android operating system and what's actually beneath. So, Android came out, just to summarize, it just came out like 4 years ago with the first devices being the HTC One introduced in 2009. The Android operating system has actually been designed, or at least the work has been designed starting from the Android Incorporated Corporation that was bought by Google in 2005, but the work has already been starting by 2003. So the system, as you may see it on today, is like 10 years old already. Even if you're only using it for like 4 years. Still in 4 years, as a developer, you have seen like 17 releases of API, which is quite incredible. They release quite often, and it's pretty good for developers because at each new API you get new features and so on. So this is really great. And one thing with the API, at least the SDK API, is that it's pretty much backward compatible. So from a developer standpoint, you just get new features, new functions, and so on, but it doesn't break everything. From the platform side, as you may see, Android is using the Linux kernel. At first it was using 2.6.25 Linux kernel, now it's using the 3.0. What you have to know is there are pretty much 3 months between each Linux kernel release, and at every release, contrary to the application, they just break everything. So not from an application developer, but from a platform developer perspective, releasing that often is not that great, because every time either the Linux kernel changes APIs and stuff, or Google modifies it, and everything is pretty much breakdown. And you have to adapt yourself so that the application developers do not see anything. And that's most of the deal. So I guess that you're pretty much familiar with this diagram. It just shows you a big architecture overview of Android. So, of course, at the really top of that, you see different Java applications, so the home application, the contacts, the phone, the browser, and of course, all the applications that you guys actually develop. Below that, you get many application services that are also written in Java. So, for different services, for the activity, telephony, the vibrator, the Wi-Fi, the battery, notification services, and so on. And on the very bottom of that, you got to see what is called the native layer. So the native layer is actually written both in C, in C++, and in Java, and some services which actually requires performances, like Surface Clinger, which is the service that actually is responsible of drawing widgets up to the screen, or Statefright, which is the multimedia layer, which requires a lot of performances. These kind of services, they are written in plain C and C++, mostly for performances reasons. And the great deal with Android is to actually be able in their framework to develop this kind of bridge between the Java world and the C++ world through a GNI layer that actually maps the different functions between the low level and the higher level that's exposed to the developers. Of course, on the very bottom of that, as most of you may know, the Android operating system is actually built upon the Linux kernel. But if you compare Android to, I don't know, any other GNU Linux operating system like Ubuntu, Debian, Red Hat, or so on, it shares the Linux kernel, but that's pretty much all about it. So any other services, daemons, servers, applications running on Android has nothing to do with Linux and can't actually run on Linux, or on the Linux distribution, I mean. If you want to start with Android as a device manufacturer, or if you have an evaluation board and you want to hack around over that, you have many sources that you can start from. The reference one is the sources from Google. So they came and they are known as the AOSP, which stands for Android Open Source Project. So they are delivered by Google, and this is the reference. They are developed in a not so open source kind of way, at least not in a community way, in a sense that developers and contributors, or willing contributors, actually do not just send codes to Google. They can, but Google just make whatever they want with it. So Google, actually, they develop in-house, and once they consider that, hey, this is prime time for a new Android release, they just drop the sources and say, okay, these are the sources, just do whatever you want with it. But Google keeps the maintenance over the sources. Different other projects exist. There is a UK consortium which is called Linaro, which is an association of different SoC vendors. So you get to find Freescale, TI, different other Chinese manufacturers. They just came all together because they are ARM users or ARM silicon vendors, and they want to join forces in order to have some higher version of Android which is already integrated, and then they can work on with extra features towards the Google version. So you may want to start with that. Of course, you may also have heard about the Cyanogenmod Bsb, which is some fork of the official Google sources, to which they have added many, many patches and features, and they want to actually support all the commercial devices that comes around, or at least all the popular ones, and create an Android version that would be a bit more open source, or at least a bit less Google dependent. You may also just have the vendor BSP. By vendor, I mean if you're buying a chip from Qualcomm or from NVIDIA or whatsoever, actually what they do is they say, okay, pick the sources from Google, and then you may have to add all of these patches that supports our board or our platform. So most of the developers, platform developers, actually work in this kind of way. So if you want to create an Android device, what you have to do, once again, as an application developer, you just have one phone or one emulator whatsoever, and you want to have your apps and your UI to be fine on this device. From a platform developer perspective, this is a phone. So it seems kind of complicated, and it seems like all hardware devices, but in the centerpiece of that, you get one SoC, which stands for System and Chip. So this is the chip from TI, which may be called OMAP3, OMAP4, OMAP5, or for Qualcomm, the Snapdragons, and so on. So it's an integrated CPU, it's a CPU which also integrates the GPU, the VPU for video acceleration, and many, many other stuff. And this one is connected to the memory, so the RAM. There is some disk space, which can be a NAND flash, which can be eMMC, or different kind of storage. You can connect different kind of sensors, so for accelerometer, compass, gyroscope, and so on. You may want to connect the audio codec and the microphone, the speakers, so on, all the radio chips like the Wi-Fi, the Bluetooth, GPS, NFC, and so on, touchscreen, a video display, also USB device, USB ports, a power management IC for handling the battery, the voltage, and so on, plus of course the baseband processor, which is actually where you plug the SIM card in order to make calls. So when you're designing an Android devices, all of these components have to be supported. And this is your role as a manufacturer to actually create all the drivers and maps all these drivers into the Android platform and the Android framework so that everything is actually transparent to you guys. So that when you just decide to, hey, I want to display some widgets, it has to display a widget, whether it is a Qualcomm chip below or TI one from Freescale or whatever. It doesn't matter to you guys, but it matters to the platform. And we have to create this kind of abstraction layer that is required for you. So if you just want to create your own device as manufacturer, there is some kind of checklist that is highly recommended. First, I recommend to be based around the reference design. So all the different SoC vendors, they create their own motherboard, and they equip them with different peripherals, and it is really great not to mess around. And if you want to have a great time to market, in order not for your phone to take 3 years to be out, it is really recommended for you to actually be as close as possible to the reference design from your vendor. And also there is one thing which is called the Android CDD, which is some guideline. I don't know how many of you guys may have heard of that or read that, but it's just guideline both software and hardware that are defined by Google, and they say, okay, if you want your device to be compatible with our system, it has to meet these kind of requirements. So, for example, this CDD for compatibility definition document, it just said, okay, your device, if you want to support Jelly Bean, for example, for example, Jelly Bean, it says that your device has to have a minimum of 340 megabytes of memory, and it has to get a minimum of 2 gigabytes of storage. Same goes for the display resolution, the graphics support, and so on. So if you want your device to be compatible, you have to meet these requirements. Otherwise, it's not even you don't even have to go to Google and say, hey, I want my device to be officially supported. They say, okay, no, it doesn't even meet the hardware requirements, so get out. And these requirements, they just go higher and higher at each Android new release. Supporting or meeting these guidelines and this compatibility document is actually essential if you want the device certification. This allows you, or as a device manufacturer, to actually say, I am compatible with Android, I am officially, meaning that all the applications that are on the Play Store are certified that they are going to work on your device. So this is really important for all the manufacturers, except if you're looking for some ultra low cost $50 Chinese or Taiwanese tablets, they really do not care about that. They won't pay for that. Most of the time they just hack around the different proprietary Google apps that they include it on the device. But if you're a real company and want to have the full support of Google and guaranteeing your users that the application that you guys wrote against the SDK are going to work correctly on the device, then you have to comply with this document. And Google has actually developed a compatibility test suite, which is called the CTS. It's a series of unit tests that is like 10,000 tests that they actually launch remotely on the device, and that certifies that for each framework, API call, and so on, the device actually behaves correctly. And so this way they ensure that when you guys just call this kind of function or whatever, the behavior that is going to be seen on the device is actually correct. And most of the challenge for different platform engineers is actually to be able to modify the Android platform to suit the needs, but still being compatible with the CTS and the CDD. Otherwise, it will break the applications. Well, Samsung still breaks some applications on some devices, but they try to maximize the number of tests that goes with the CTS. So a bit more about the Android kernel. So as I said, the Android is based on Linux, the Linux kernel. The Linux kernel is developed in an open source and community way, and Android is not that much. It took like nearly, Google has added many patches for Android, or to the Linux kernel for Android to work. These patches are called what we call the Androidisms. So these kind of patches, actually, they've tried to integrate it officially in the Linux kernel, because every time you have to port the modifications, so at some point you just want them to be officially in the tree. Most of them have been integrated upstream by the kernels 3.3 to 3.5. So it took them 4 years to actually be able to integrate them. And if you remember one of the first slides that I showed you, all the devices right now, even the Jelly Bean 4.2, are still using 3.0 kernel. So none of them are using the official trees. Still, Android has added many patches to the Linux kernel. So one of the most well-known and one we created most of the flame wars on the Linux kernel list is the wake locks. I'm pretty sure that you guys in your application have ever used the wake locks. The goal of the wake locks is because of a fundamental difference of power management policy between Linux and Android. Linux, as it has been designed, was mostly for desktop and servers. So it's like my computer is always on, and sometimes I just want to put it in suspend. On Android, you're running on a battery. So the policy is like, I want my device to be always off. And sometimes I want to keep him alive. So that's why you guys just acquire some wake locks, preventing the device to be shut down. So you may imagine that when you're trying to merge this kind of philosophy, it doesn't suit that well. Other things that was really well designed in the Android system was the Ashram and the binder system. So Ashram is a shared memory allocator, and binder is some kind of IPC systems that has been designed like a message bus, and which works at the kernel space. Of course, I don't know how many of you guys have ever heard about the binder. Quite a few, because it's kind of used in the applications, but it relies on the low-level sessions. So binder, as I say, is a driver. So essentially what it does is allowing IPC system calls between a client and a server. It acts as a message bus because the client just sends some data and someone may just receive them, but they are not really directly connected. What it does is that the server actually tells the kernel that, hey, I want to register some function calls, and this is done through the service manager. And every time a client just needs something, it just makes some calls to the kernel through the binder driver and just asks the service manager, who am I going to send information? And actually, the information is not directly sent between the client and the server, but it's sent from the client to the kernel, and the kernel routes the data and the message and the functions to the server. And one of the good things with that is that they use the Ashram memory, so the asynchronous shared memory design that they have created. They use it so that the client just creates some shared memory pool where it puts the data. And then it doesn't send the data back to the other application, but it just sends the ID of where in the memory the other application has to get the data. And this allows actually the system to avoid a lot of memory copy, which are quite CPU intensive, and it actually makes the system quite fast and responsive for that. Otherwise, your system, not being an x86, but being an old ARM system, even if they are becoming more and more powerful, it just waits too many times, just taking data, marshalling the data, sending data across the memory, copying them back, demarshalling, and so on. So they just want to avoid this kind of behavior. Also, one thing that is pretty much different for the Linux kernel towards the other systems or GNU Linux systems is that usually you have one kernel designed for one device. So one smartphone, one tablet, and so on. And it's not a PC where you say, okay, you have 10 or 12 USB ports, and I want every guy to be able to plug in every kind of device. So you don't have these drivers as a module, but everything is quite built statically, except for the Wi-Fi drivers, which are just loaded or unloaded when you just decide in the settings application to actually start the Wi-Fi or not. They are also done so because the Wi-Fi usually requires a firmware, and depending on you having selected to use Wi-Fi as a client or as a station or as an access point, you may require some different firmwares, and so loading the modules a bit differently. So once again, this driver's policy is quite different from what you may experience on your regular Ubuntu, and but still, at the end, all the drivers, there was a talk about that on yesterday, all the drivers per se are actually Linux drivers. And all of the manufacturers, what they are trying to do when they are creating a new board and they want to debug the board, they're usually creating some micro Linux distributions and just trying to set up the sensors and the screen and so on. And once everything works, they just put it back to Android. Because the regular embedded Linux offers so much more debugging capabilities than what Android does. Android user space is also quite different from what you may experience on the regular GNU Linux. So one of the big differences is the C library. So the C library is the interface between the kernel and the applications, the C and C++ applications, that maps all the codes. So on Linux, usually you get something which is called the glibc for GNU C library. And the Google guys, they decided that this library was too much bloated and consumes too much memory and some security issues and so on. So they decided to take another one. So the reason might be good, but what it means is that the API is not POSIX compatible, and the ABI, so the binary compatibility, is not the same as the glibc. So in practice, what this means is that no applications, no pre-built binary that you may find on your Linux distribution may work as it on Android. So if you just imagine that you have some super daemon or whatever that runs on your Linux server or your Linux desktop and you just copy and paste it on Android, it doesn't work. Also, what you do, you get to take the sources and you have to compile them against this Bionic library and then port it back to Android. But even in the API has changed, so sometimes you also need to modify the source code of all the free open source software that you may find. You have to adapt them, the make files you have to be adapted, and sometimes the C code also have to be adapted for Android. So this is kind of bugging because Sometimes you guys, when you develop Java applications, you may need some GNI native library, and you say, okay, this is some open source project that I find which seems to be quite nice and seems to implement what I need. But you have to take care that this open source project has actually been ported to Android, or you have to do the job by yourself. Among the different restrictions that you may see, they have removed the System 5 IPC because they have the binder. They have removed the support for locals and wide characters. They have removed the C++ exceptions. They have a custom DNS resolver. So many stuff are really quite different from the regular Linux. This is something that you may, not you may, but you are well known aware. They also have introduced the system properties. So system properties are a series of strings in the property equal value form, and this is like the Windows registry actually, and it just allows the different applications, whether they are C, C++, or Java based, they just ask the system to get the value of one property. So you may have one, for example, defining what is the density of your screen and so on. So they just ask the system for that. All these properties are actually staying in memory, so every time you reboot the device, these kind of properties just get out. They also have many SQL databases. Secure and system tables are the most well-known. And one of the big differences with Linux is the user space hardware abstraction layer, which we call the HAL. The HAL is actually one layer above the Linux kernel and drivers and below the Android framework. The purpose of this library is to create some kind of user space drivers that has to be implemented by all the device manufacturers. The goal of this HAL is to connect to the GNI layer and then to the application layers, so that when you guys just want to get the coordinates of your GPS or want to get the position of the compass, the accelerometer, and so on, you just have one API and you do not care what is the hardware below and how it works. And the goal of this HAL is actually for every device manufacturers to say, okay, when the application developer asks me for this, then I have this specific implementation because my hardware has to be driven some specific way. And so they create this abstraction layer. And the HAL is a set of dynamically loaded shared libraries, so they are in the form of .so files. Google provides an API for that, so it's in hardware, lib hardware include hardware directory within the AOSP sources. And with this API, they say, okay, this is all the functions that you, device manufacturers, have to implement in this SO file so that application developers are happy. And then they use the different system properties, for example, the Aero hardware or the Aero product board, to say, okay, this is some board from TI, so I can load this HAL. And this is a board from Qualcomm, so this is another HAL that I have to load. This table sums up quite a few HAL modules that actually exist in the Android systems. So as you may see, most of the hardware peripherals that we've seen on the picture before are actually implemented with HAL. So you get one for the audio, for the frame buffer, so if every time you want to draw on the screen, you have to do something. You have something for the GPU with the GFX allocator and the hardware composer. You get one for the camera, for the Wi-Fi, the GPS, Bluetooth. So every time you want to access to your hardware devices, there comes the HAL. One of the problems with the HAL is that it may not be a problem depending on who you are, but it allows the device manufacturers to actually close the source of the HAL. So it's fine for them because they can protect all their IPs they got. But on the other end, you just got a binary blob and you have no idea what it does. And the problem is the Android API for the HAL it moves and it evolves quite fast. So usually when the device manufacturers just give you the HAL for Jelly Bean 4.1 or Jelly Bean 4.2, when Google decide that they release Jelly Bean 4.3, if they have modified the API, then you get to find the new HAL. And usually this is the reason why it's so hard for Cyanogen, for example, to actually create custom ROMs and so on, because they need these proprietary drivers from the manufacturers. They have to find them somewhere, and they have to ensure that the different manufacturers actually are willing to give this HAL. So sometimes you speak about programmed obsolescence. For example, you get some chips that actually could work on the next Android, but the manufacturer decided, okay, this chip is already 2 generations old, and even if they could, they do not want to release the HAL, and so you just say bye to key lime pine, for example. And that's just because the hardware manufacturer just doesn't want to support the chip anymore and and force you to move to the next generation. And for that, you can't do anything. It's just, you just have to rely on the willingness of the manufacturer to actually provide you something. A few more words about the Android systems and the Dalvik VM. As you all know, Android runs Java. It's not completely true. It's, you write Java code, but it's Dalvik code, which is actually executed. This is done by, at the compilation time. There are also some other possible optimizations through system properties when you want to tune the Dalvik virtual machines. When you want to integrate the different peripherals, as a device manufacturer, once again, I made quite a list of all the things that you have to do for supporting the different devices, with some kind of difficulty label. So as you can see, sometimes you have to modify the bootloader, which is kind of bias for x86 systems. You may have to modify the kernel and the different drivers. You have to modify sometimes the Android HAL in order to provide your own SO files. And sometimes you also have to modify the framework. For example, for the video codec, it's so badly designed that for every new VPU that wants to accelerate video, the Android framework and the stage fright framework has to be modified to take into account the support for the new chip. So many things have to be modified behind all the platforms in order for you guys to be happy. One more thing about the Android initialization, which completely differs from the GNU Linux systems that you may have seen. Android has its own init, so it's different from the one that you got from Ubuntu. Actually, what it does is start its own language where you can actually say and do whatever you want. So you can create new virtual devices, you may start new daemons, start applications, and so on. Every device has its own init. What init does at first is starting the Zygote process. I don't know how many of you ever heard about the Zygote. Okay, quite a few. So, for instance, it's also present in Chrome or Chromium. Zygote is actually the mother of all Java applications. And it's quite nicely designed because this is one super daemon that loads up all the Java classes at once. So you get one big instance of all the Java framework in one single process. And every time you want to create a new application, then it's actually a call to Zygote, which just says, I want to create a new application, and so just spawn a child, which means that Zygote contains all the classes, and your program will only take a subset of this one. And this avoids spawning new memory blocks and so on. And so your application is actually started quite fast because it's just a child of this Zygote with some references to the parent. So this is quite fast and quite performant, and it avoids you needing 4 GB or 8 GB of memory on your device. Though you may still need 4 GB in 2 years, but anyway. And then it also starts the different managers and the different flingers. So as I said, the Android init is quite, it's a text file, so you can put whatever you want in it. There are different sections for the early init, for the initialization, for the pre or post file system stage, different kind of stuff. So as I said, this is one other example of init and all the applications or servers that it may start. Once again, these are really Android specific and none of them can be found in a regular Linux systems. Other things that I want to have a quick word about is the graphic layer. So the graphic layer, as you know, there is something called Surface Flinger. If you're familiar with GNU Linux, there is something which is called Xorg or X11. It's pretty much the same thing. Surface Flinger is one window compositor, and so all the applications, they just want to create some surfaces. So if you have one application, which is the launcher, it creates a background, you get some system top bar, you get some other widgets. All of these widgets, they just go through Surface Flinger. And then it's Surface Flinger job to actually compute them, create the composition, and put that and draw them on the frame buffer. So once again, how it works, it's whether it is 2D or 3D, what it does is actually creating surface objects, and all these surfaces just go to Surface Flinger, which then uses the HAL in order to be able to draw what you want, whatever the device that's actually did all the mapping and so on. Same goes for the sense keys, or if you've got a regular USB keyboard, for example. What you want to do is that if you click on this kind of weird house that you got on your device, and you just want to map it to the home key. And this is designed and defined with this kind of file. But if you want to change it and just say, okay, just hit back instead, then you may do that. It would be stupid, but you may do that. The other layer is, once again, not the best success in architecture, in Android architecture design. Why I'm saying that is because many of you guys, as application developers, experience some issues. iOS developers have less issues about that, but you get latency issues and real-time issues because you just want your sound to be heard much quicker or faster than it actually is. And I will not go into details about that, but the Android audio stack is actually composed of many, many direction layers. So once again, you got the applications and the Java framework. You get different audio managers, services, and so on. Then you got the GNI layer, which does some OpenGL implementation. Then you get many other implementations which are done in C and C++, which does a lot of minor code. This is done in the big media, and on bottom of that, you get Binder, you get the audio flinger, which is responsible for routing the different calls that you made and the different audio data that you want to send. They have to be routed, maybe resampled into some other bit rate or some other frequency and so on. They have to go across many, many other layers. They can be pre-processed for automatic gain control, echo cancellation, noise suppression, and so on. And then at the very, very bottom of all of that, you got the HAL, and you got the driver and the hardware. So imagine all these layers that you want to came across each time you just want to beat. So this is kind of crazy. And the goal, once again, of the HAL is actually to map the application developer side from the hardware. So, for example, this is not really a driver, but part of the HAL. You may find that if your chip, audio chip is called Wolfson Micro 8958 in this example, you just want to say, hey, these are the supported devices. So I guess that all these names and names probably rings a bell to you because they are pretty much what you see in the SDK. So what you need to do in the HAL is that when someone in the application just say, I want to output sound to the wired headphone, then at the very bottom of the HAL and all the drivers, we have to say, okay, on this chip, on this device, on this configuration, the headphone or the speaker or whatever is actually triggered by moving this configuration and these pins on the SSC and so on. So we have to do this kind of mapping so that you guys, when you say, okay, just output something on the microphone, not on the microphone, but on the speaker, then it means something on one device, maybe it's something else on another device, but for you guys it just doesn't matter. You just leave something on the speaker. Here, once again, one more configuration file. The multimedia layer, as I said, is implemented by the stage-wise implementation. It was done previously by the open core implementation. What they could have done is, already very late, I guess. What they could have done is actually using some GStreamer or FFmpeg libraries, which are really well known in Linux, and they were much, much better than stage-wise. But they did so mostly for licensing reasons, and Google likes to re-implement everything so that they are not GPL compliant. Same goes for the multimedia. One of the big challenges is that, as you can see, you have so many layers to cross, and you guys just want the 60 frame per second UI. So if you just consider 60 frames per second, it means that you have 15 milliseconds to process every frame, whether it is video or just plain graphics. And in this 15 milliseconds time frame, you have to cross all these layers. You have to also handle all the other application that runs. You have to handle the audio, synchronize everything. And this is once again one stage-wise architecture that you guys are interested into.
And at the very bottom of that, you still got these purple squares that the device manufacturers actually have to implement so that it's kind of fast and you guys can do whatever you want, and as slow as it is, you must ensure that the low end is fastly processed. I'm just going to conclude quickly with the network layer. Android supports many networks, things like the Bluetooth, the Wi-Fi, and many stuff. It doesn't support SNet, which is kind of stupid because it's the most simple interface to support. In my company, we have done some changes and some patches for ICS and also for Jelly Bean, which if you have some board which supports SNet, for example, someday the Nexus Cube or something, it's ever going to be released. We have made support for that. The challenge was that as a Linux kernel release, you just need a driver and it just works. The thing is that Google never thought of adding it into the framework. So you get the connectivity manager and connectivity service and so on, and all the applications, they just ask for this kind of service and say, am I connected to the internet? And it has no clue of SNet, so even if it is, you just say, no, I'm not connected, and all your applications will not work. And if you see some Chinese tablets, for example, some of them have some SNet ports, and it kind of works. But actually, the only thing that works is the browser. The reason for that is that the browser is actually using WebKit, which is written in C, C++. So it just do not care of Java, and it just works because it's Linux-based. But for any other real Java application that is correctly coded and runs using the connectivity service and managers, it just doesn't work anymore. So this pretty much concludes my talk. As I said, the DroidCon was the first for me because I'm not an application developer at all. What I wanted to introduce to you was that actually Android is based on Linux, but it's not the GNU Linux that you may know of. And even if the drivers are pretty much compatible, this is kind of new specific domain of expertise, and you need some really good experts if you want to create your own Android devices. It's not that easy. So I'm not saying that the application developer's job is kind of easy, but device manufacturing is kind of hard too. And most of the job and the job that we do and the real success of the job is to actually unify and create this HAL and this seamless experience so that you guys, application developers, do not have to care about the hardware and how it actually works. So this is a completely complex task, and I just hope that with this talk and all the articles that I've made on all the bibliography books that you may find, you may just understand that when you write applications, just imagine that if you can spare the CPU a few cycles and so on, it will be great. Because when you just say, okay, I'm going to draw something, there is so much work to be done by the hardware and all the other layers that have been crossed. So when developing applications, just think that there is something below, and if you can minimize the amount of effort it is, then everybody is going to win. So that's pretty much all about this talk and about me. So if you get any questions, I'm not sure that we got the time. Maybe 2 questions, because we got sponsored by APC and we got some evaluation boards. So there are 2 to be given. It's pretty much all for me. If you want any more details, you may just hit my name on LinkedIn, on Twitter, or Google+, or just ask me some more questions. So there's going to be 2 questions, if any. There is 2 evaluation boards to win. I'm not keeping anything, so anyone who just ask a question wins the board.
How old are you?
Anyone who asks an Android platform question wins the board. Yes?
Do you think that all the driver might be rich and pleasure to make a new version of the device?
So the question is whether all the drivers need to be published to create a new version, a new public version of Android which supports everything. Yes, because I believe in open source, and the more free drivers there are, the less it is. It's not in Google interest to do that because they do not want to support all the devices. It's up to the manufacturer's job to do that. They usually support up to 3-4 devices, mostly the Nexus series. Usually when you just check the AOSP sources, at every new release they support new device and discard the old ones because they do not care anymore. So supporting the drivers would be great, but this is one thing that you also need to have free and open source have, which is likely not to happen because for licensing reasons, well, manufacturers just want to keep their IP.
Google provides Jelly drivers for components to meet the components.
So does Google provide generic
Hardware Jelly drivers for.
So Google doesn't really provide generic hardware. They do the Nexus series, and they usually rely on the manufacturer to provide them the drivers. That's the only thing to do. And usually for the different drivers that they have some websites where they publish in SO file if you want to rebuild your own device, but it's still proprietary. So you can rebuild it, but you still have no idea how it works. That's going to be all. So
bonsoir. Bonjour.
Bonsoir.
Hello. Je m'appelle Alexis, je travaille chez Google.
Didier, je travaille chez Sql.
Aujourd'hui, on va pas pouvoir vous parler beaucoup de mobile, on va parler surtout de back-end et pourquoi c'est vraiment une bonne idée d'en avoir un pour mettre un vrai moteur de Ferrari dans les Ferrari que vous développez sur téléphone plutôt que vous roulez en Ferrari, un moteur d'étranger, un bon cloud avec de bons services, ça va être intéressant de se rencontrer avec quelque chose qui s'appelle le mobile back-end starter.
Il faut mettre en combien?
Donc l'objectif c'est de créer une application comme ça. Ici on va même pas aller jusqu'au bout du serveur, on va même pas utiliser l'image. On va avoir une application multi-utilisateur évidemment qui va permettre de faire du chat, qui va permettre de partager du chat et tout ceci est stockage dans le cloud, dans la solution de NoSQL de Google, dans le data store. Tout ceci sans développement côté serveur, avec une infrastructure qui est déployée pour vous, qui utilise une architecture anti-trust, avec ce qu'on appelle des endpoints, et sans gestion d'infrastructure, parce que tout ceci est hébergé pour vous. Et donc tout ce qui est cloud, toutes les propriétés du cloud, notamment d'élasticité, entrent en jeu. Petite cerise sur le gâteau, l'idée c'est de ne pas avoir à saisir de mot de passe, et pour autant d'avoir quelque chose de sécurisé. On va vous proposer tout simplement de réutiliser les comptes qui sont créés, qui existent sur votre téléphone. Donc, on va s'appuyer sur quelque chose qui s'appelle Mobile Backend Starter, quelque chose qui a été annoncé à Google I.O. il y a quelques semaines maintenant. Comme je l'ai dit, elle a pour objectif de vous permettre de démarrer sans écrire une seule ligne de code, quelque chose qui est tourné dans App Engine, donc c'est la solution cloud, type plateforme de service de Google. Technologie à partir des endpoints qui permet d'exposer de la logique métier sous forme d'API REST. Une authentification intégrée de bout en bout, c'est-à-dire que c'est le même utilisateur qui côté client utilise l'API et qui va stocker ces données côté serveur dans le cloud storage, dans le data store. Et enfin, un système de notification intégré, donc Google Cloud Messaging, vous pouvez connaître, mais avec simplement de la configuration. Et côté serveur, on a toujours cette règle qui est de ne pas écrire de code serveur.
Tout d'abord, on va démarrer par quelques mots autour de REST. Alors, qui connaît REST? Ah, on va pas.
On passe
à la suite. Donc, juste quand même quelques mots sur les REST et les API autour. Donc, c'est quelque chose maintenant qui est très largement utilisé par tous les acteurs de la data économie. Ça sert beaucoup comme protocole de communication entre ordinateurs. C'est un principe d'architecture qui est implémentable au-dessus de HTTP, qui permet d'identifier des ressources. Voilà. Ces ressources sont identifiées par des URI. Donc il y en a deux types. Il y a des choses qui permettent de ramener des collections et des choses qui vont nous permettre de ramener des éléments. Donc ça c'est quelque chose d'assez important. Et ce qui est très important quand vous faites du REST, c'est de bien penser à votre API, de bien la construire, parce que voilà, c'est quelque chose qui va vivre pendant des années. Et si vous l'avez mal conçu, vous allez le payer cher maintenant dans les années qui vont suivre. Moi j'ai une API qui est là depuis 4 ans et au début je l'avais fait un petit peu pour m'amuser comme ça et j'ai un peu payé ça quand j'ai ouvert à d'autres services. Et là je suis en train de complètement la réécrire et de la penser correctement voilà, de manière à ce que ça facilite l'ouverture au monde extérieur en fait. Donc c'est assez important de bien penser ces API. REST c'est un protocole qui est sans état. Ça veut dire quoi? Ça veut dire qu'entre deux requêtes, il n'y a pas de relation. J'envoie une requête, le serveur va oublier, quand je renvoie la deuxième requête, le serveur va avoir oublié que j'ai envoyé une requête. En gros, c'est orthogonal, tout ce qui est stateful. Dans le reste, il va y avoir 4 actions standards, je veux dire, qui s'appuient bien sur les verbes HTTP, le post, le get, le put et le delete. Ça ressemble assez du point de vue des 3 autres verbes qu'on utilise beaucoup dans le domaine de l'informatique de gestion, qui sont le print, le read, le update et le delete, connus sous le terme CRUD en fait. Ce qu'il faut retenir, c'est que dans le post get et le put et le delete, tous ces verbes n'ont pas forcément un sens par rapport aux actions qu'on mène. Par exemple, faire un post sur une URI d'une ressource, ça n'a pas de sens en fait. C'est ce que j'ai montré ici. Donc là, si vous faites un post sur l'URI d'une ressource, normalement, votre backend doit vous envoyer un post, vous faites plutôt sur l'URI qui pointe sur une collection, ce qui va vous créer un nouvel utilisateur. Donc c'est assez important de respecter de mettre en place, quand vous construisez votre API, un ensemble de règles qui vont aider les gens qui l'utilisent à un peu l'intuiter et à bien la sentir. Voilà, donc aussi très important, ce qui est souvent un peu oublié des développeurs back-end, c'est que l'idée c'est de s'appuyer sur le protocole HTTP et d'utiliser les codes retour de HTTP pour envoyer du sens au consommateur de l'API en fait. Donc vous avez le droit, quand vous avez même le devoir, quand vous faites une API REST, de renvoyer des 404 si l'utilisateur essaye d'accéder à une ressource qui n'existe pas en fait. De la même manière, si ça se passe bien, le fait de renvoyer un code retour de sens, ça a beaucoup de sens. Donc souvent, historiquement, on construisait, on est plutôt des espèces de requêtes qui renvoyaient des messages et on se disait on faisait du REST. Non, REST c'est pas ça. L'idée c'est de coller à l'idée du HTTP et d'en utiliser un petit peu tout ce qu'il propose. Une autre chose qui est très importante, et surtout si vous construisez une API qui va durer, c'est penser aux versions. Quand vous publiez une API qui coupe derrière, vous n'avez plus le droit de la modifier. Ça ne veut pas dire que votre API ne peut pas évoluer. Au moment où elle va devoir évoluer pour des nouveaux besoins, à ce moment-là, il va falloir avoir prévu la notion de version. Donc il y a plein de manières de faire des versions. Une des bonnes pratiques, c'est de les mettre dans les IORI. On va s'adresser à des API avec certaines versions et on va retrouver ces notions de version dans les IORI. Pensez à ça. Tout ce qui est authentification, donc c'est quelque chose qui est assez complexe, je pense qu'on peut dire le mot. Enfin, tous ceux qui se sont frottés un petit peu à Watt, des cicatrices, si on veut dire. On est bien content qu'il y ait des choses qui arrivent autour, mais voilà. C'est pas parce qu'on fait du reste qu'on ne va pas penser à la sécurité. Entre autres, par exemple, vous publiez votre service, si vous laissez vos API ouvertes, d'autres clients, d'autres applications Android pourront venir consommer votre API. Vous pouvez, ça peut être souhaitable pour vous qu'il y ait des gens qui développent de nouvelles applications qui consomment vos API ou pas. En fait, vous pouvez à la fois mettre des mécanismes qui vont valider le fait qu'un utilisateur a le droit d'utiliser votre API, mais aussi qu'une application a le droit de consommer votre API. C'est bien ces deux niveaux à laquelle il faut penser. Voilà, donc une ressource, quand elle va être consommée par un client, elle va respecter des formats. Donc maintenant, le format qui est en train de s'imposer autour de REST, c'est JSON. La raison principale, c'est que on a beaucoup de clients JavaScript qui consomment les API REST, et donc le format naturel pour exposer des ressources à destination d'API JavaScript, c'est du JSON, et donc c'est un format donné qui est un peu en train d'envahir tout l'écosystème. Voilà. Donc, ça, c'est un peu tout ce qui est théorie. Et Google, depuis un an maintenant, propose ce qu'ils appellent les endpoints. Donc, c'est un système qui va vous permettre de créer une application avec un jeu d'API. Donc, c'est la manière dont vous allez exposer vos API. On va utiliser la plateforme que Google utilise aussi pour utiliser ses propres API. L'idée, c'est vraiment de bénéficier du savoir-faire de Google pour exposer vos propres API. Donc, tout ça, c'est packagé sous une technique de déploiement qui s'appelle les Cloud Endpoints. Donc, ça arrive avec Google Engine. Donc, l'idée, c'est de construire des applications que vous allez pouvoir, des API qui vont pouvoir être consommées par tout type de clients. Donc, avec Endpoints arrive deux choses, c'est la possibilité de diffuser votre service, mais aussi des générateurs de code qui vont vous permettre de targeter certaines plateformes. En fait. Donc c'est souvent pénible de coder le boilercode qui va consommer une API. Avec Endpoints, vous allez pouvoir générer ce boilercode de manière à l'utiliser tout simplement derrière sur les plateformes iOS, Android et puis JavaScript. L'idée de Endpoints, c'est de créer des backends qui vont être capables de